In last lecture, we have seen what is matrix, different matrix operations, their complexity, disadvantages of matrix, and as a solution, the use of sparse matrix. This example was given. I hope everyone has tried that. So here is the solution of that. The matrix which was given, it was 8 by 8 dimension matrix where 8 rows and 8 columns were present, and in that very few non-zero terms were present. Very few, here we can say only 8 non-zero terms were present. So we are saying that instead of storing that in two-dimensional array, we can store that by making use of representation of sparse matrix. So in sparse matrix, we know that we are defining a triplet which is going to store row number, column number, and only non-zero value of that element which is present in that matrix. So here we can see the same 8 by 8 matrix we are representing by using sparse matrix representation, where 0th row, it is specifying you number of rows, how many rows are present, number of columns, and number of non-zero terms in the given matrix. And then in every row, it is storing row number, column number, and the non-zero term. So this way, we have made reduction in the space. So here if you observe, to store 8 by 8 8 by 8 matrix, we may require, and it is an integer matrix, integer data it is storing. So 64 element it is storing, and if we assume that I require 2 bytes to store one element, so we can say 64 into 2 bytes to store one element, 128 bytes it is going to use. But now here we can see only 8 elements via non-zero terms are there. And to store one element, we are taking 3 values. Its row number, column number, and its non-zero value. So we can say one entry will require 6 bytes. And as we have 8 entries, so we can say total 48, 6 into 8, 48 bytes will require to store this particular array, which was sparse matrix, or very few number of elements were present. By using sparse matrix representation, we can reduce this much amount of memory to store the information in your 2D array. Now we have to see operations. We have seen that by using representation in some different form, we are reducing the space. But now we need to see about the operations also, whether we can reduce time as well as space for executing the operations on this same with this same representation method. So now in this lecture, we are going to concentrate on the operation which is a sparse matrix addition operation. So we know that matrix addition we can perform. We have two-dimensional two matrix with same number of rows and same number of columns are present, then only we can perform the addition of two matrices. Same logic we are using for performing sparse matrix addition also. And then we are going to see the complexity of performing sparse matrix addition. So consider here we have two normal matrix we have, where 15 number of rows and 6 number of columns are present in these two matrices, and I want to perform addition of these two matrices. So first of all, we are checking whether rows of A matrix and rows of B matrix are the same, and columns of these matrix and columns of second matrix, whether they are same. If its order is same, then only we can perform the addition. And then as per our normal algorithm, we are reading one by one entry from both the matrices and we are performing addition. So it will start from the 0th row, 0th column, and it will end up to last row and last column data. So first it will just write one iteration will be requiring to keep the track of row number, and one will be to keep for every row what is the column you are considering. So keep track of column number in every row. So one by one, we are going to take the entry from every row and column, and we are going to add that, and then we will get the resultant, which is the addition of that element. Here, 0th row, second column is having value, non-zero value 1. Here, though here 0 value is present, so 1 plus 0, it is 1. It is going to store that value finally in the resultant matrix. Similarly, for all the elements, it will perform this. This way we are doing addition, and that's why we can say the complexity of matrix addition, it is order of n square. Here n is representing number of rows or columns and columns which are present in that matrix. In our case, 15 rows are there and 6 columns are there. So we can say 90 times this particular loops are going to execute, and it is going to perform the addition of these two matrices. So in general, we can say its complexity, it is quadratic complexity. As my n will grow, its complexity will also increase quadratically based on how many number of rows and columns are present. So now we will see the same matrix, suppose we have, and we want to perform, we are representing it by using sparse matrix. We know that very few non-zero terms are present, so we will decide that same matrix I will represent by using sparse representation. And now I want to perform the addition. So whether after representing in the sparse matrix, whether really with efficiency I can do the addition operation, with the less complexity I can do, or with the same time complexity I can perform the addition, that we have to see. So consider that same matrix we have represented in the sparse form. So we can see at the 0th row we are mentioning order of matrix, number of rows, number of columns present in both the matrices. In the second column, 0th row, second column, we are mentioning how many number of non-zero terms are present. And then afterwards, as usual, it is in the sorted form. First, it is on the row, and then it is on the column. We have made all the entries, non-zero entries in your sparse matrix. Now we want to perform the addition. So ultimately, the result will be same. But here, the process what we are going to follow, that will be different. So now how we can perform? First condition is what? When we can perform the addition of two matrices, two elements, if their row number and column numbers are same, then I need to do the addition of that non-zero term. But otherwise, it may happen that their row number and column numbers are not matching. So I need to add that entries as it is in my resultant matrix. But we know that after performing addition also, my whatever matrix I'm going to get, that also should be in the sparse form. Means also it should be in a sorted form on rows, and afterwards it is on the column. So just I cannot perform that, just check values from this matrix, values from this matrix, wherever they are matching, just do the addition, put it in this your resultant sparse matrix, and then perform adding remaining entries. That is not possible. So that's why we need to see, we need to define proper way for performing addition. So how we are doing that? So what we do, first we are checking whether the order of two matrices are matching. If they are matching, then we will just see, we will just take one counter variable, or we may say one pointer, which is going to point to first matrix. Maybe that pointer variable, I will say it is I, and another that is J. It will give me entries from the second matrix. Now what I will do, I will start from I need to check whether rows and columns are same or not. But if they are not same, then what to do? So I'll just first check whether rows number are same. If row numbers are same, then I need to check what is the column status. What is the column of this entry in the first array, and what is the column in the entry in the second column? Are they matching? They are not matching. So if they are not matching, then what I will do, which one will be the smaller one? The smaller one, obviously, if it is not present here, means in my original matrix, 0 entry must be present in that. Means this entry, it will directly go to my resultant matrix with this particular value. So I will just create one matrix where at the first location where my pointer variable may be k, I am saying that is the pointer variable. At that location, I will just copy entry from the first matrix, which is from the 0th row and second column into resultant one. And only I will increment I. So I will increment it and I will come to the next location. Similarly, I'll increment the k also because next entry I need to add at the next location. So now again I will check what is row number and what is row number of second matrix. Are they matching? Yes, they are matching. And now this time their columns are also matching. Means in both the matrices at 0th comma 5th column non-zero element is present. So I have to perform the addition of its non-zero terms. So I will add this entry in the resultant one 0, 5 and 2 plus 2, 4. So now I can consider that I have taken entry into consideration from A matrix and B both. So I will increment both the pointer variable. I will come to next location. At the same time, J will also come to next location. And as this entry we have added, K will be also incremented so that next entry, whatever will come, that will come in the next Kth location. Again, I will continue this. It will say row number and row number, they are same. At the same time, columns are also same. So it will copy. So it will say in the both matrices, non-zero elements are present. Do the addition of that non-zero element and put it in the resultant one. So again, it will make that 1 and 2, it will become 6. Both I and J will be incremented. Now here I will point to the entry, which is the first row and fifth column, and J will point to first row, fourth column. K will be incremented. Here I am going to make the addition of next. So now this time rows are matching, but now column from the second matrix is having smaller value. So this column, this entry will be copied into resultant one and only J will be incremented and K will be incremented. So 1, 4 will be added in the resultant one. J will come to the next location and K will come to the next location. Again, I and J, it is going to compare. So now rows itself are not matching. So it will see if rows are not matching, which row is smaller one. So if this is smaller one, so obviously we can say from this we can conclude that in my second matrix, for first row, fifth column, no non-zero entry is present, means this will be copied as it is directly to the resultant one. So 1 and 5, this entry will be added in the resultant one. Only I will be incremented and K will be incremented. Again, I and J entries, it is going to check. So 2, here 3 row number, here 2 row number. Row number is smaller. This row number is smaller. So this entry will be copied in the resultant one. So this way, how we are doing? First, we know that sparse matrix, whatever we have created, they are in the sorted form. So we can say that these are nothing but the ordered list. Okay. So I have 2 ordered arrays and I want to perform as good as merging of these 2 sorted array. So I can make use of merging concept where we say that in merging, we will just take one entry from the first data set, one entry from the second data set, whichever will be the smaller, that we will add in the resultant one, and only that entry will be incremented, its counter will be incremented. Again, we are comparing whichever will be the smaller, that will be added in the resultant. If both are having same values, then both will be added in the resultant one, and then increment will be performed in the both the array. So same logic we are using for the sparse matrix also. Here we have seen the example. So how we can write the algorithm for this? So we can say, suppose for this algorithm, we are saying add is my function. To this add function, I am passing two objects of sparse matrix, where in every object of sparse matrix, one two-dimensional array is present in which three columns are there and some n number of entries are present. So here A and B are the two objects where SM is matrix, two-dimensional matrix present. Post condition, after doing this addition, I will get the resultant matrix, which is the addition of these two sparse matrices stored in a M object. I, J and K, these are the just counter variable, or we may say they are for traversing purpose, we are making use of these variables. So now I have to repeat. Here we have seen that one by one entry we are reading from both the matrices. This we are continuing till any one of the matrix is not completed. Any one of the sparse matrix is not completed. I have to continue that. So what I will do, I will just say that my condition for while is unless my I counter variable, it is less than whatever non-zero terms present in first object, whether this condition is true, and J counter variable, it is less than whatever non-zero terms present in the B matrix if it is less, because in SM of 0, 2 as well as 0, 2 in first matrix, non-zero terms are present. So if these values, my I counter variable and J counter variable, are less than what are the length of that sparse matrices, number of non-zero entries in the sparse matrices, I have to continue. And what I have to do? First, I will check status of row number. So row number I am going to get from the ith row, 0th column. In that, row numbers are same. So if my row of first matrix is smaller than row of second matrix, then what I am saying, you just copy A matrix content in the resultant one. So row from the A matrix, column from the A matrix, and non-zero term from the A matrix, you copy in the resultant one. Now, if an increment, just I counter variable and K counter variable. Now, it may happen that row number in A is greater than row number in B. So B is smaller. So I need to copy entry from the B into resultant one. So similarly, I will just copy from B, as B is having J counter variable. So from Jth row, 0th column, that is the row number from B, column number from B, and non-zero entry at that place, it will copy in the resultant one. Similarly, I will just increment J and K. Now the third case, it may be third case, it will be A and B row numbers are matching. So if they are matching, obviously I need to check status of column. So what is the status of column? Where we are storing a column in ith row, first column. So jth row, first column. So I will check whether A's column is smaller or B's column smaller. Column number is smaller. So if A's column number is smaller, then copy the entry from A into resultant one. As we have done in the first case, similar we are doing here as well, and just incrementing I and K. Now the reverse case. Rows are same, but B's column number is smaller. So here we can say B's column number is smaller than A's column number. So copy the contents from B matrix, B sparse matrix into resultant one, and increment only J and K. And now third case, that A row number and column row A's and B's row number are same. At the same time, A and B column numbers are also same, then copy anybody's row number and column number into resultant one and do the addition of non-zero terms, and then that you copy in the resultant one. Do the addition, and that addition will be copied in the second column of kth row, and increment all I, j and k. Now we are doing this activity unless any one of the sparse matrix is not completed. Now it may happen that for one of the matrix, lesser number of entries are there. So, and that is finished early. So now the few entries are remaining. So now you have to copy that remaining entries from that particular matrix to resultant. Already they are sorted. So I don't have to do anything. Already they are sorted on row number and column number. So as usual, if second matrix is completed, in first matrix few entries are remaining. So just whatever are remaining, I is pointing to that latest entry which is right now going on. So from that position, you copy all the contents from the first matrix into resultant one. Maybe first matrix is completed, first matrix is smaller, and all entries from the first matrices are completed and not in from the second. So in that case, it will execute this. So out of this loop, any one of the loop is going to execute. So maybe this loop is completed, or the A's entries are completed, or B's entries are completed. Accordingly, it is going to copy remaining entries by using these for loops into resultant one. At the end, we are storing. So once I have done the addition, obviously after performing addition, it is going to change non-zero terms in your resultant one, because here we can see in the first matrix, 15 non-zero terms were there. In second matrix, 14 non-zero terms were there. Now, out of that, few were common. So, they have performed addition. So, after performing addition, based on the k value, we will come to know how many number of non-zero elements are now present in resultant one. So, for the resultant matrix, its order is going to come same as your A and B, but the number of non-zero terms, they will be k minus 1. So here you could see in our example, which we have considered. Here 15 entries were there in the matrix A, 14 entries were present in the matrix B, but after performing addition, only 19 entries are coming in the resultant one. Means few entries are common, and because of that common entries, they have performed addition and only one entry is coming in the resultant one. So after performing addition, what last entry we are doing at the k position, based on that, we can update how many number of non-zero terms present in my matrix. So this way, we are performing the sparse matrix addition. Now here we want to analyze what is its complexity. What is complexity of sparse matrix? As we have seen for the matrix addition, we say that it is a quadratic n square complexity. So whatever m number of rows are there into n number of columns, that many number of iterations it will require to execute the addition of this. But now here, if we consider now this while loop, it is going to execute number of times unless any one of the matrix is not completed. So if we can see in our A matrix, 15 entries were there. In B matrix, 14 entries were there. So unless these 14 entries are not completing, it is repeating one by one from the this loop is going to execute that many times. And now whatever are the remaining entries there, that will be copied by using next remaining two for loops, which are these for loop. Any one of them, it is going to execute. So this loop, they are going to execute if more number of entries are there in the first matrix, then this will be executed. m minus n time, or this will be executed n minus m time. But ultimately, if we could see complexity, how many time total number of elements or execution number of iterations are going to perform, out of m and n, whichever will be the smaller, that many times it is going to execute, plus m minus n, or as m is smaller or n is smaller, if m is smaller, then 2m minus n, or we may say that it is at the max. If I'm considering that 15 entries are there in the first matrix, 14 entries are there in the second matrix, and if they are not at all matching, all these 15 are distinct and 14 are distinct, means in the resultant one, total 29 entries are going to come. Means my loop, it is going to execute maximum 29 number of times. So we can say the loops which we have written in the sparse matrix addition, its complexity, it will be at the max, it is going to execute order of m plus n. So m are nothing but non-zero terms in the first matrix, n non-zero terms in the second matrix. And in the best case, if all are matching, then obviously only whatever will be the lesser value that it is going to consider. So in general, we can say the complexity of sparse matrix addition, that we are reducing it to linear order of n, where this n is nothing but, in worst case, it is m plus n, where m is the m and n are the number of entries, non-zero entries in your given matrix, non-zero entries in your sparse matrix. So this we can say. Then regarding space complexity, we can say it is constant, because we are not doing any additional space. We are not requiring to perform the sparse matrix addition. Whatever matrix we have defined, only, and resultant one already we have defined, only that much memory we will utilize for performing addition, for storing the addition of sparse matrix. No additional memory is required to perform the sparse matrix addition. So we can say sparse matrix addition space complexity, it is constant, while time complexity, it is order of n, which is nothing but order of m plus n, or we may say it is a linear time complexity. So we can observe that by converting your matrix into sparse matrix, space obviously we have reduced, because with that we have seen only non-zero terms we are storing. At the same time, for addition of normal matrix, we require quadratic complexity, time complexity, n square time complexity we require. But for sparse matrix addition, we require order of n, which is nothing but m plus n in the worst case. So this is all about sparse matrix addition. You may go through with this example. Matrices are given, represented by using sparse matrix representation. Perform addition by applying the algorithm which we have just now discussed, and store that resultant matrix, store that addition in the resultant matrix. In the next lecture, we will discuss about sparse matrix transpose. Thank you.